Hello everyone. In this video we will see how we can implement loop control structures in the ARMv7 assembly language. Plus we will also see how we can index or traverse through the arrays by using the loops. Alright, so let's first start with the example code for writing for implementing the factorial, like computing the factorial family number, and let's see after when we get used to the loops how we can use the loops to traverse through the indexing with the arrays. Alright, so first start with the factorial program. So let's say I have a file factorial.s. alright, and I have some text section which is code section. Alright, so here is my main section. So for example, I have some number n which I can move in any of the register. Let's say I have r. Alright, and I want to compute the factorial of, let's say, 6. Okay, so 6 is that any number n for which we want to compute the factorial. Alright, and then we have second number which is r2. Alright, and we have moved the value 1. So the idea is to compute the product in this register for the factorial, and in each iteration we are going to subtract this value. Alright, and then multiply with this one. So at the end of the loop we will have the answer stored in r2, and then we can move that answer into r0 so we can see our output on the console. Alright, so let's say we have this number now, and we want to compute the first product. So how are we going to do that? We have mul instruction, if you remember. Alright, so we can write, let's say, mul r2 comma r1 comma r2. Alright, so we cannot write r2 here because these two registers should be different according to the instruction set. Alright, the limitations. So on the next instruction, now what we want to do is that, because this is the first product we have computed here, so the 6 multiplied by 1 we have here now. Alright, but now we want to multiply the next number by subtracting this one number. Alright, in the next iteration. So what we are going to do, going to subtract 1 from this number. Alright, so I will say subtract r1 comma r1 comma 1. So I will subtract 1 in each iteration in this value. Alright, and then what I'm going to do is that, because this step is going to be repeated in a loop, so but if this result is reached to the value 1, alright, I should stop my iteration, because multiplying by 1 means the same answer. Alright, so in this case, if this condition has reached, so I will just simply exit. I will go to the exit section. Alright, which will have the last ending instructions of our program, which will terminate it. Okay, and before that, after this instruction, in case this this comparison is not true, alright, it fails, like r1 is not equals to 1 yet. So what should we do? We should jump back to this previous line so that the multiplication and product is again, it can be executed. So the product will be computed each time this iteration will run. Alright, so I will put my unconditional jump here. So I will say b. I'll name the section factorial underscore s. Alright, so which is this line, of course. Okay, so after when this comparison will fail, it will jump back to this line where the multiplication is executed, so that the factorial product will be going to be executed. Alright, and it will be computed in the r2 register. Alright, so now what about the exit section we have here? So what we can do here is that we can move our value which is computed in R2. Alright, we can move that in this register of R0. So when we can when we will execute our program on the console, so we can see our answer. All right, so let's say move R0 comma R2. All right, and then I will have instruction bxlr, all right, which will terminate the program, all right, or give the control back to the operating system, in other words. So I'm going to save it. All right, and let's now try to compile it. So what we can do, we can edit our previously made makefile here. All right, so we can just simply run it. Okay, so we have factorial here, factorial, and we have all. Okay, should be careful in spellings of the file, that should match with each other. All right, and the sections we are defining here, and in clean we will remove the factorial executable link file. Okay, factorial. Okay, so now save it, and I'll say make clean. Okay, and now I'm gonna make it again. So I have now these files created. I can check that here. So here's the factorial.o, and here's the factorial. All right, so let's run factorial. Go. So it's showing the answer 208. So what happened here is that the value that is displayed by this particular command, that basically ranges from 0 to 255. So since the answer of 6 factorial is 720, so it has just simply wrapped around the answer here. So that's why it has given us 208. But if you will run this code in the GDB, all right, if we debug that there, so you can see the answer 720 here. But before that, if you want to check the answer is correctly computed, we can try for some small value as well. All right, so let's say I can change the number to 5. So 5 factorial is 120. All right, so I'll just change it here and save it. Now I can make it again, and then I'll execute it. So here you can see the 120's answer. All right, so for example, now we want to check the answer in the GDB. all right, so let's go there and check the correct answer for the 6 of the factorial that we should see there as 720. all right, so I'll say GDB /factorial. So it is started. So let's start the debugging now. Okay, now disassemble and see where we are. So it's showing the first 2 instructions that are basically in the main section. Okay, because the next instruction is coming in the next section, which is the factorial _s. That's why it is not showing us right now. All right, so what we can do is here we can execute the first instruction, which is basically moving our number 5 here, and then we can change the value of R1 at the runtime here. Okay, so I'll say step I. all right, so I can check the values info registers R1. Okay, so we have 5 here, so let's change it to 6. all right, so the R2 R1 equals to 6. Okay, and now check the value. So R1 has now value 6. Okay, and we have current the next execution that is going to execute is 103D4, this instruction. all right, in case you want to see it, just type the disassemble command and see here. Okay, so it's pointing here. All right, so now execute it. All right, and now you're in the factorial underscore s section, where the first line, which is the product line, that is going to execute. Again, we want to see the first line of this section. So that is now this multiplication instruction, which is going to compute the product of this factorial numbers. Okay, so let's execute it here. Or maybe now what we can do is here we can apply the breakpoint. Let's say yes, we can apply our breakpoint at this particular section, all right, which is the address, this one. Okay, so I will say break static 0x0000103 EC. Okay, so and what we can do is that we can simply continue, so it will keep running until it reaches this section, which is the exiting section. Okay, it has continued and has now it has come to this exit function. Okay, now we want to see the value of our product, which is basically in this computed in this R2 registers, so we can see that. So let's say info registers R2. Okay, so now you can see that the factorial of 6 is correctly computed. Okay, it was also correctly computed back then, but again the problem is with the with that echo command followed by the executable command, that it shows the numbers limited to from like 0 to 255. So it cannot show the number above that. So if the number comes above that, it simply simply wrap around it. Okay, and you can see this since this answer is correctly computed. So now the next instruction is to move this value into register R0. all right, so if you just execute it, okay, and you see the value of R0 as well here, so you can do that. Okay, and if you want to check the value of R1, which has reached here, so it's probably 1, because when this value is 1, definitely on that particular point this section has stopped continuing and has jumped to the exit section. So these are the correct values we have here. And now the last instruction we have here is to terminate the program, like by giving the control to OS. So we will just say continue and enter. So our now code is executed successfully. So that's the way how you can implement the control structure, how you can perform the repetition of work over the number of instructions. So that's how you can repeat it. So this was just one example, and you can you can implement multiple problems using the control structure, specifically those problems which are related to the nature of this problem that needs some repetition in that as a logical instructions. All right, so that was for how to implement loops. Now we'll see for the arrays that how we can implement them for traversing or indexing with the loops, with the help of loops. All right, so let's quit this one, make another program. Let's say arrays.s we have here. Okay, so again first I will have now my data section. Okay, I'll say b align 4 bytes. Okay, and now I can name the arrays. So I have first array A, and this is word. Okay, and let's say I have the array of 4 elements. All right, so 1 2 3 and 4. Okay, and then I have another array. All right, so this is also word size. Okay, and I have answer, sorry, the values here I have are, let's say, 0. Okay, so what's what do we want here is that I want to simply copy these values into this array. So I will copy the values of array A into array B, alright, just like these elements, and we will check that it's going okay. And apart from this, the other way to declare the array is like we can use the skip keyword here, alright, and we need to specify like how many bytes we need to skip. Okay, so if you see, this word size value is 4 bytes in size, each value. So how many bytes are total here? There are 16. So we say, let's say we want to skip the 16 bytes for the array B, so it will allocate the this much size of the array B as well. So when we will copy our answer into the B, we can see that the values are correctly moved there because we have correctly skipped the bytes. If this value will be wrong, the answer will also be wrong, alright. So we always need to see like the alignment and the spacing of the elements are correct according to the bytes of the word, alright. So that was the dot data section, and now let's move to text section. Okay, and we can also put here the dot b line 4, alright, and now the global main here, alright. So before writing main again, we need to declare the addresses of A and B as well, just like we did in the one of the last videos and the programs for the when we implemented the arrays, alright. Sorry, the memory addressing. We did that when you declare the memory or variables, you need to declare the address as well, alright. So let's say I declare address underscore A, and let's say dot word A, and the for address B is colon dot word B, alright. Now what this the first thing that you do is that we should need to load the address of the array A, alright. So I'll say ldr r1 comma address underscore A, alright. So at this particular line, this is holding the value of the address of the array. So when we say the address of A for the array A, so the address is always the address of the first element of the array which it points to, alright. So if we want to say like where is the next element is placed, so the next element is placed on the next 4 bytes, alright, and the third is on the next 4 bytes, so on and so forth. That's how the array is basically, the elements are placed in the memory, alright. So the address of array is basically the address of the first element of the array variable element, okay. So this will points to this particular value here, okay. And then what we want to do is that we want to load the address for the B array B as well, because we want to copy the contents of array A into B, alright. So we have another register, let's say R2, and it has the address underscore B, okay. Now what we want to do is we want to copy these values, okay. So since maybe the memory to memory movement is not allowed by the architecture, so what we can do is that we can use another register to copy the values, and then we can move that into the memory location, alright. So instruction is ldr r3 comma r1 dereference. So you need to dereference the address so that first so you can access the first element here, and which will be moved into the R3, alright. And now we want to store this value into the first location of the B, alright. So I can just for the convenience, I can just add the comments here that this is actually 0, like this. It's declared here in the memory, alright. So and actually there will be some junk values here as well, okay, maybe not 0. So now I can use the store instruction to store the value into the memory. So store r3 comma r2. Alright, so it will again dereference the first location here, and it will move the content of r3 of which is eventually the content of the first element of array A, and copy on the first location of the array B. Alright, so that's how it's done. And now so that was for the first element. So what about for the rest of the elements? If you want to copy them one by one, so we need to move to the next address of this array A for the second element, then for the third, and for the fourth, and so on and so forth. Alright, so I need to so this was the address of array A, which was first time loaded here. And if you want to move to the second element, now we want to add the 4 bytes, the next 4 bytes into the address, so we can so the pointer or the address, this will point on this, the second element. Okay, so I'll say add r1 comma 4. So the 4 bytes are added. So the next, now the address is basically added to this particular to the value which was first time loaded, and now it's pointing. So this particular address is now it's pointing to at this this little element here. Okay, the second element of the array. All right, and similarly for the array B, because we also want to move this address to the next location here, so we need to add the 4 bytes here as well. Okay, so add r2 comma 4. All right, so that's how it's done. Okay, so one thing we need to see that we need to stop this iteration at some point as well. All right, so what we can do is that since we know that elements are 4 in this particular case, so we can set some counter register. So we have move, let's make r4 as the counter register to keep the count of the iterations. So currently we have, let's say, 4. all right, and we will subtract this value after each iteration is executed, or this particular set of instructions executed to copy the elements. We will subtract 1 from this each time. So r4 comma #1, and then we will compare it with 0. So like if it reaches 0, this means that all the elements are processed. Okay, like all the elements are copied on the next array. So this means this is, if this equals, so we should jump to the exit section, exit_s, and then we can put here an unconditional branch or jump, so that it can jump back to this previous location from where it can again start the process of copying the elements from one array to another. All right, so b and say copy_s, the name of this section, so where it should be placed. So and the placement of label is also important. All right, and in this case and in every case where this type of work is being executed. All right, copy_s here. So and now again at this particular point, now it will load the address. So it will load the value from the r1 by dereferencing this particular value. So it will copy it here in this r3, and once it is copied in r3, it will copy this value here. All right, because that's the address of this which is placed in now r2 and r1. All right, so this will again execute, and that's how it will keep repeating it. Right, so what happens if we put this label back here before this instruction for r4? So what will happen is that because also you are subtracting this value by 1. So but if you, in each iteration, if you will keep copying the value 4 here, so this loop will never end. So that's a kind of a logical error here, that you subtracted here 1 to decrease the iteration count, but then you again move back the value 4 again, so this will then never end. Alright, so that's why the placement of the section label is very important in every case. Alright, now we come to our exit section here. Alright, and we'll simply write the exiting instruction, another control to OS, which is bxlr. Alright, so I'll just save it, and now let's change the make file again. I'll say it now arrays. So once this is successful, correctly done, the make file should be created. Alright, now I should save it and exit it. So let's say we have make clean. Okay, and I say make. Okay, it's not created. Alright, so now what we can do is that we can just go straight and debug the program to see the answer there. So this is GDB /arrays. Alright, so I'll say start. So I can disassemble it. It's pointing here. Alright, so these were the addresses that were declared after the main section in the file. So you can see the address of array A is this one. Alright, but in case if you want to check it yet, then you can simply write like this, like B pointer ampersand A. So you might need to check that. Oh, what's the correct command here? So let's see that. Okay, so the correct way is this static int ampersand A, and then how many elements that you want to see here. Alright, so that is the array A. Alright, and similarly if you want to see the array B. Alright, so what we can do is that we will execute the first iteration here, and we'll see the changes in this array B specifically. Alright, in case you want to check the address of A and B that it matches here, so you can simply say PA, yeah, P ampersand A, which means the ampersand points to the address here. Okay, so 21024 is the address of the array A. Alright, and So this was the address of that place where we declare the addresses of A and B. So that points to those locations here. Okay, so these are not the addresses of A and B, so it is basically the addresses of those locations where the address of A and B are placed, like after the main section. Alright, so in case if you want to see the address of B now, okay, so you can see that this is the address of B here. Alright, anyways, if we just want to see the result here, alright, so let's disassemble it. Okay, step I, okay, so if you want to check the values of R1 and R2 specifically, and R4 as well, let's say, so R4 registers R1, R2, R4 and R3 as well, because we are using that registers as well. Alright, so you can see that this is the address of array A and array B. So you see the difference in these values of these addresses. So that is the difference of 16 bytes exactly. Alright, and because this is the hexadecimal numbers, so of course, so like adding 10 is basically like, so it makes 34, because 16 is 10 in hex. Alright, so when the 16 bytes are added in this address value, so that makes to 1034. Alright, so that's correctly displaced. So after 16 bytes, the address of the array B basically starts. Alright, so this is the element, so this was the address of the first element of the array, which was this one, and this was the address of this particular place of the array B. Alright, so the first element. So that's the difference between, like, after adding 4 bytes to 4 bytes to 4 bytes, that makes 16, which is basically 10 in hex. When you add that in address, so this makes 21034, like adding 10, basically adding 16 in decimal terms. So this add to 21034. So that means that's the address is correctly aligned in the memory, like, which is the alignment of 4 bytes from the locations. Alright, so now currently we are in this section copy S, and let's say we can disassemble it. Alright, so we are currently here. So in this particular location, the value of R1, basically value of array A first element, will be dereferenced and loaded into the R3 register. Alright, so let's step I, and now see the values of registers, specifically R3. So you can see now R3 is now changed. The value 1 from that array is now copied into the value copied into the register R3. Alright, and what was the next instruction? So next instruction is to store the value which was loaded in R3 to the location of the first element of array B. Alright, so let's execute it. Okay, now it has come to this particular instruction, to increment in 4. Okay, but before that, now let's see the status of the arrays again. So this was the instruction. Okay, so you can see that the 1 is copied. So for A, which is 1 2 3 4, because since we are not changing array A, so that will stay same across the execution of the program, but array B will change eventually, because these elements are going to be copied into the corresponding location here. Alright, so first the 1 is basically copied into the first allocation. Now the second element 2, that is going to be copied into the next iteration. Alright, so now in next instruction you can see the that we are going to add 4 bytes in the address, so that it will point to the next location in the arrays, in both of the arrays. All right, so I'll say step I. Okay, now check the values of the registers. So you can see, so initially it was 21024 and it was 21034. Now we have added the 4 bytes here, so this is now 21028 and 21038 the address of B. So now it is basically pointing to so R1 is basically pointing to this particular location of the array A, which is this one, and for R2 this is the location of the second element. All right, so what's the next step now? All right, so R4 was used for the counter as the counter register to maintain the count of the iteration. So as one iteration is now completed, so we have decremented the value by 1. All right, so this instruction was executed. Okay, so now it is going to compare that it has reached to 0 or not. All right, okay, so this comparison was failed. That was not true. All right, because R4 value is not 0 yet, so it is now going to jump back to the section of copy S, which is the instruction 103 DC here. All right, okay, now it has pointed to this instruction, so we can exit it. We can execute it, these first two instructions. All right, now it's pointing here. So by execution of these two instructions, the second element of array should be of the array A, that should have been copied now in the second element place of the array B. All right, so now if you want to see the status of the arrays now again, so you can do that. Here's our, so that was for array A and that was for array B. Okay, so now you can see that the second element is correctly copied to the second location of the array B. So when all the iterations will execute, so by the end of the time, what will happen is that the 3 and 4 will be copied correctly here. All right, so now if you want to just continue the instructions till we reach is exit underscore S section, we can just simply apply the breakpoint here. So break static, so the address is this one for the exit section. You can say break 0x00103FC. all right, so the breakpoint is applied now. Now continue it. Okay, and now check the status of the arrays again. So that's the array which is unchanged and B is here. So you can see that the elements are correctly copied from the locations of array A to the array B. All right, so that's how we can use the indexing here. All right, so I can just simply now continue it again, so that program can be exit. All right, and I can quit it. Okay, before stopping the video, what else we can do with arrays is that, like specifically in regards to indexing. So what we have done here is that we have currently have changed the base address. So the address A here that we loaded here, it was the base address of the array A and array B, which is declared here. All right, So, and in each iteration we have actually changed the base address by 4 bytes in each iteration. All right, and uh, and after that, when you reaches the end of the program, the base address is basically changed here in the R1 and R2 registers. So if you in case for some problems you maybe not want to change the base address in each iteration, so for that purpose what you can do is that you can also use another register, all right, for the indexing purpose, all right, and in which you can add the 4 bytes, or like you can add that register here and particularly at this place, all right, like for example you can write here plus any other register, let's say R5, all right. So if you want to use the R5 as the index of the array, so the index again here will be the 0 based, all right, because if you will put it like 0, so that is going to change the if you will move the index 1, that is going to change the meaning at all. So indexing is again 0 based, and the next index is at plus 0th location, and the third is at plus 8, then plus 12, so on and so forth, like you're adding plus 4, all right. So what you can do is that here you can start this R5 with, let's say, 0, and you can after the execution of these instructions, all right, specifically, so in case when you are adding so you don't need to add 4 bytes in R1 and R2 registers, which are basically the base registers. You can simply add 4 in R5, okay, and this instruction can be avoided then, all right. That's how you can do that as well, all right. So let's check if this works. So I'll just make a minute, okay. So yeah, I have error here for by using this register. Let us check again. Okay, so you might just need to add this apostrophe here and it should work. So say vim, where is s, and let's add the apostrophe here. Let's see if it works now. So make clean and make so again we are having error, so let's check that again. Okay, so let's get this done correctly now. So the correct way is just simply putting the comma instead of plus sign here, instead of saying like we are adding something which is not, and remove this apostrophe as well, but doesn't make any sense. So now let's save it. Okay, and now let's make green and make, alright, now it's done. So I'll say now GDB dot slash arrays. Okay, now start it, and now then disassemble it, right. So if you just want to see the correct output, that the values are correctly copied by using this new method, like you're just adding the index, not changing the base address. Alright, so you can just first let's run the first 4 instructions. Okay, alright, so we are in this section now. Alright, and if you want to see the values of the array that we were using, alright, so let's initial stage of these arrays are the ampersand a, and to see 4 elements, this is the one, and for b here we have this one. Alright, so what I can do is that, like, to quickly execute it, I'll just put the break here at this point, alright, in the exit section. So let's say break and static 0x 0103fc. alright, so now break is there, and now I can continue running it like all iterations, and it will keep changing these values here from array b. So 1 2 3 4, like in these 4 iterations. Alright, so continue here. Okay, and now let's see the state again of the arrays. So array a should be unchanged and b should be changed. So here you go, the values are correctly copied by using this new method here. That if you want to add these values by, let's say, r5, so you can just simply say 5 here, r5 here. Alright, and it will add the next 4 bytes here. Alright, so that's how you can use this new scheme of addressing here in this assembly language of ARMv7 as well. Like if you want to change the indexing, you can do that, and you don't want to change the base address, this is unchanged, so you can also see that. Alright, so and for registers we have r1 and r2. Alright, so this is the base address. So base address is always the base address of array is the address of the first element of the arrays. Alright, so that is unchanged in this scenario. So that's how we do that, and in case if you want, you can confirm that here that it's exactly that address. You can always print the address on the console here. So in the GDB debugger, so say b ampersand a. Okay, so you can see this value here, and for b it's right there. Alright, so that's how we use it. So the values are correctly copied by using this new method of indexing. Alright, so you can also use that in case there's problems comes up where you don't want to change the address of the base address of the arrays, but you also want to traverse throughout the arrays, like by adding from one element to the other element, jumping from one element to another element. Alright, so that's how you can do that. You can use this indexing scheme. Alright, so that was for today. I can exit this program by just continue it. Alright, so in next video we'll see what do we have. Probably we'll talk about the functions. We'll see how we can create functions in the assembly language here. Alright, and in the meanwhile you can practice these things with your device at home, and in case if you want to have any questions, you can also ask the question in the comments. Okay, you can reach there, and if there's anything you want to add, if you want to add some suggestions, so you can do that as well. Alright, so just don't forget to subscribe to the channel, and please share these videos and share this channel with everyone in your circle as well. So that's all for today. Thanks a lot. Bye bye. Alright.